Hey guys, how's quarantine going? What was that? Oh yeah, me too, totally. I miss having labs in school too. It's just like sitting at home doing stuff on the computer, like go out for a run, but I miss being able to do stuff hands-on. Oh, hey, why not? That's a great idea. Totally. Okay, let's do a physics lab. This should be awesome. Oh, which one should we do? Oh, okay, I know. Let's do something with circular motion. I've got the perfect thing. Okay, so what we're gonna do is make have a string going through a tube with as little friction as possible, and we'll have a weight at the top and a weight at the bottom, and the weight at the bottom will be heavier. So if you just held it up, the string would slide through and the heavier weight would go downward. But if you get the top part circling around, then we'll get it to be in equilibrium. Huh? No. Okay, but centrifugal forces are not a thing, dude. Yeah, I know when you're on a merry-go-round or whatever, you feel like you're being pulled to the outside. That's just inertia, because your body wants to go in a straight line. So you would just go forward and fly off in a straight line, but you're being constantly pulled towards the center. So your mass pulling you closer to a straight line. That's why you feel like you're brought outward. So that's what's happening with the rock too. The top rock wants to keep going straight. So in order to keep it from flying away, there's a tension in the rope, and that tension's also acting on the lower weight, which is what holds it up. Okay, yeah, so let's try it. Let's see what happens. That's not an experiment though. That's just us playing with weights. So what we could do is derive a theoretical relationship between the period of the top weight circling around and the length of the rope. So let's do that. Let's derive the theory for it. Oh my gosh, this is so cool. I'm glad we had this idea. Feel free to follow along, make your own equipment, take your own data, write out the equations, and let's do this lab together. This is going to be awesome.
So the first thing we're going to want to do is draw a free body diagram for mass 1, the lower mass. So it's going to have gravity acting downward, which is its mass times acceleration due to gravity, and it's going to have tension acting upwards, which means that the tension in the rope is equal to the first mass times acceleration due to gravity. Then let's do the same thing for the other mass. Again, we're going to have gravity pulling downward, but this time the tension force is going to be acting at an angle. Let's call this at angle theta from vertical. Because mass 2 is experiencing circular motion, we know that its acceleration must be v squared over r, where r is the radius of that circle, and v is the linear motion tangential to it. Then we know that the force causing circular motion must equal mass 2 times that acceleration. But the only thing that this force could be is the horizontal component of tension. As such, we can say that that horizontal component of tension is equal to this force that we found to explain circular motion. Now we can combine these two expressions to get m1g sine theta equal to m2 v squared over r. But what really is r? So if we look at the setup of the system, we basically have a right triangle with angle theta, hypotenuse equal to some length of string, and base r. Therefore, r is L sine theta. So we can rewrite the expression that we got before, and now we have m1g sine theta equal to m2 v squared over L sine theta. So now we can rewrite this expression to solve for v squared, and we get sine squared theta times m1gl over m2. Or alternatively, we could write this as v equal to sine theta square root of m1gl over m2. Now we're getting somewhere. So we've got m2 just traveling around in a circle, which takes a period of time which should be equal to 2 pi times the radius of that circle divided by the speed at which it's traveling. So let's just plug in that speed. So if we plug in v and r, we get period equal to 2 pi square root of m2l over m1g. Or we can alternatively write this as t squared equal to 4 pi squared m2l over m1g. And here we have it. We have a relationship that we can test. So let's do it. Let's go set up our experiment. So first we'll need a reasonably low friction tube. I made mine by disassembling several mechanical pencils. I wanted to tape them together, but these little nubs were in the way, so I had to cut them off, which proved harder than anticipated. After that, the tape fitted on pretty smoothly. I added a little bit extra just to make sure that this really wasn't going to bend during the experiment. So there it is, threaded through. Next, I needed to mark different lengths at which to measure. I marked points at the top and the bottom of the stick, with the string held taut between, so that I would have more visual cues to make sure I was staying on point. The corresponding markers are black, blue, pink, green, and red, all in pairs. I then taped rocks to either end, a heavier one for the bottom and a lighter one for the top. Next, we'll need to know the weights of both of the rocks with the tape on them. Came up with 76 grams and 26 grams. Lastly, we need to measure the length of string from the center of the top rock down to where the string will go into the tube, so the top of the two paired markers with the string stretched taut. The bottom rock's going to want to pull down, so I need to swirl it at just the right rate to keep it up without making it rise higher and higher. Notice if I slow down, it sinks down. If I speed up, I can get it back up. Or not. Right there. Okay, it's steady. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I then found the start and end times for each set of 20 repetitions from their points in the video and marked them in a spreadsheet. With start time in seconds, end time difference, I found the time for one period by dividing that difference by 20. So that gives the time that it takes each time to go around in a full circle. But remember, the relationship between period and length was not linear, so we need period squared, and so that's what this is. And then we just graphed these two columns to get this graph, which shows period squared versus length of the top string. And I have a regression line here, which is set to intercept at 0, and it gives us a constant of proportionality, which comes out to 0.0135. That's seconds squared per centimeter of length. Okay, so from our theory that we derived earlier, the constant of proportionality should be 4 times pi squared times m2, which was 26 grams, divided by m1, which was 76 grams, and also divided by g, which I'm going to do is 9.8. So notice that we need to have our units correspond. G is in kilograms and meters. Our weights are in grams, but I'm not going to worry about that because one's on the top, one's on the bottom. They're going to cancel each other out. What I do want to worry about, though, is that our lengths were all in centimeters, and G uses meters, so we're just going to divide by 100 since G is in the denominator, and we get 0.01378.
Alright, so we got all our data analyzed, and from what we measured, it looks like our experimental proportion is only 2% away from the theoretical, which is pretty decent given our not very exact equipment. So, did you have fun? Yeah, I'm glad you did. See, this was such a great idea. I'm glad that we had this idea. You know, if you want to have more fun like this, you can always hit the subscribe button and make sure you hit the bell next to it so that we can come back here and do more awesome labs together. Yeah, well, thanks. That's great. Okay, I'll see you then. Bye.